Hey there, Calc folks, back here with what might be our last video looking at some techniques we use for calculating derivatives here, folks. And what I hope to share with you in this video is a pretty powerful technique, I might say. A pretty powerful technique when we have really a complex combination of derivative rules, right? Combination of derivative rules maybe involving product with some quotient with some possible chain rule, all mixed together in some variation, right? A technique that might work well for us is what we're going to see here in this set of notes, folks. So let me bring this up. What we're talking about is what's called logarithmic differentiation, folks. It's a really what we might think of as powerful technique we can use to find derivatives when we're looking at complex functions, right? Functions that are complex combinations of other functions and functional types of behavior, right? And derivative rules. For example, here's an example, right? We might consider finding the derivative for this complex combination, right, of functions here, where this complex combination involves a little product rule, right? If you see in the numerator here, we have x times the sine of x. This is all being divided by x plus 1 squared, which is a little quotient rule being applied there. And if you think about x plus 1 being squared, you might even consider that being a little bit of chain rule with that squaring, right? If we don't expand out the x plus 1, we are going to have to approach that x plus 1 squared's derivative with a little bit of chain rule. And although not necessarily a tricky derivative, it could be rather tedious to set this up and to perform the calculation and avoid potential error, right? Another process we could use is what's called logarithmic differentiation. And it is pretty efficient in its technique. And it's kind of interesting in the fact that it does basically rely pretty much upon one derivative result, as opposed to relying on a combination of several derivative rules. We really only rely upon fundamentally maybe one or two derivative rules. Now, I should be careful saying that because we do mix up the rules, but there's one dominant rule in this process that kind of works outside a product or that quotient or that chain rule. So let me bring that into view. What am I doing here? First of all, what we do note is that this would require a pretty complex combination of rules here to calculate, as we had noted. To simplify the process, we could use a process called logarithmic differentiation, and we're setting that up now. And we can rely upon this process, and we do rely upon a rather useful derivative result, and that is this result here. For the differentiable function y equals f of x, if I consider finding the derivative with respect to x for the ln of f of x being the natural logarithm of our function f of x, the result will always be f prime, the derivative of f, divided by f of x. The derivative will involve the derivative of f prime of x, the derivative of our function y equals f of x, being divided by the original function f of x. For this form, ln of f of x. And this is going to be a really useful result in what we call logarithmic differentiation. This is the primary derivative result that we rely upon. Now, there does require a little bit of setup in the process in order to apply this rule. Now, to begin with, I do prove the rule. And I do go through a little chain rule to show you this, right? If we consider y equal to the ln of f of x, letting u equal f of x implies y equals the ln of u. We can then say du dx is equal to f prime of x. We can talk about dy du being 1 over u. And since u is equal to f of x, and the derivative being the product of these two results, we can end up with f prime of x over f of x as our derivative result, right? So from chain rule, we end up with 1 over u times f prime of u for these two individual derivatives, which produces this quotient of f prime of x divided by u. And again, because u equals f of x, we can write this as f prime of x over the value of f of x, all right? For the derivative of y with respect to x, what we might, again, take note was the derivative with respect to x for the ln of function f of x, right? It does give us this derivative result, right? This is going to be a really useful result. Now, as I said, this is going to require a little bit of setup. All right, if we bring that setup in to our example, the way that we begin our setup is we apply the natural logarithmic function to both sides of our equation. We're going to apply it to the left-hand side, the ln of y, right? And the equation we're working with is this equation here. We apply the natural logarithm to the left-hand side y, and we're going to apply it to the right side, the x sine x divided by the x plus 1 squared. We're going to apply that ln to both sides. Now on the left-hand side, right, or what we start with here down here is the right-hand side. So let's start there. On the right-hand side, when I apply the ln to this argument here, what we have to remember are our rules of logarithms. The rules that state that the logarithm for a quotient can be written as a difference of two logarithms, and the logarithm for a product can be written as a summation of two individual logarithms. And any power seen on a logarithm, as we might see here for the ln of x plus 1 squared, that power can be brought out in front as a constant multiple inside of our logarithm. Remember your law of logs. All right. We can rewrite the log of x sine x over x plus 1 quantity squared using our law of logarithms to reduce the ln of x plus the ln of sine x minus 2 ln of x plus 1. Where if you notice, each of those involve the form the ln of the f of x, right? Or the natural logarithm of some function f of x. In this case, it's just x. In this case, it's the sine of x. And in this case, it's x plus 1, the linear function. Right? On the left-hand side, if we apply that natural logarithm, right? I should say, so then we have the ln of y is equal to this statement here. Rewriting the right-hand side of this statement, where then we apply the derivative. And applying the derivative to both sides, right, we will apply it to the left, to the ln of y, where we know the result for that, right? So we set above the derivative with respect to x for the ln of y. Ooh. Hold on, do I have an error here? Oh, yeah. Duh. We're thinking of y being our function of x, right? The ln of y. So if we let y be a function of x, if we think of that as being some function of x, right? Then we can write the left-hand side as f prime of x over f of x, right? And that is my next step, right? If we assume y equals f of x, the derivative with respect to the ln of y becomes the derivative with respect to x for the ln of f of x. And that's where I'm going to produce the f prime of x over f of x. We're going to see follow up here on the left-hand side. Now on the right-hand side, when I apply this derivative operator, it will distribute itself across the sum and difference. And in this difference here, that 2 is going to play the role of a constant multiple. And as it applies itself to each of those terms, what we notice is each of those terms is also in the form of a derivative with respect to x for the ln of f of x, where this rule in general will apply specifically in those cases. Right? So if we distribute that derivative, we will have the derivative of each individual function. Inside that sum and difference, we'd have the derivative with respect to x for the ln of x, which we know is just 1 over x from our derivative rules for natural logarithms. When it distributes itself to the ln of sine x, well, we know that's going to be the derivative of the sine x over the sine of x from the rule above. And what's the derivative of sine x? That's cosine x. So the derivative with respect to x for the ln of the sine x is going to be cosine x divided by sine x. We're going to see that in the next step. And here we're going to have minus 2 times the derivative for the ln of x plus 1. And the derivative for the ln of x plus 1 is going to be the derivative of x plus 1, which is just 1, divided by x plus 1. So it's going to be negative 2 times 1 over x plus 1 in the next step. And if we bring that into view, we will see that, right? So we said the derivative with respect to x for the ln of x is 1 over x. The derivative with respect to x for the ln of the sine x is cosine x over sine x, because the derivative of sine x, right, fits this general form. The ln of some function, this function being the sine x, is the derivative of that function, so the derivative of sine is cosine, over that function, which is back over the top of sine. That is always the derivative result for the ln of some function. And we apply that rule here. The derivative of x plus 1 is just 1. And we put that back over top of our function x plus 1. Okay. So what we end up with is on the left, f prime of x must equal 1 over x cotangent of x minus 2 over x plus 1. So when we think about the derivative with respect to x for the ln of y, the derivative of this result seen here, what we notice is it's given by this result seen here. It'll end up implying on the left-hand side, we simplified this to f prime of x divided by f of x. And on the right-hand side, we just showed the derivative for this statement involving the natural logarithm simplifies into 1 over x plus cotangent of x minus 2 over x plus 1. Where what we're looking for is the derivative of y with respect to x, which is this f prime of x sitting right here. That's the value we're seeking. And with a little bit of algebra, we can actually multiply both sides by this denominator f of x, multiply the left and the right by this denominator f of x, and it'll move it to the right-hand side over here into the numerator. So when we solve for f prime of x, we would end up with this result here, multiplying both sides by f of x. It'll move this f of x up into the numerator on the right-hand side. Now, that f of x, we want to remember, is our initial function. I do think I say next, since f of x is our value of y, which equals x sine x divided by x plus 1 squared, and f prime of x is equal to y prime, we can replace the left-hand side with y prime must be equal to this argument. And let me go ahead and highlight that with a group. That is our f of x. Right, this argument right here that came from our initial question that started this lecture, right? What is the derivative of that? And what we're finding is the derivative of that is what we call this value f prime of x. This is our dy dx, and I think we said let's find dy dx. So let's state it that way. And we can end up saying dy dx must then be equal to x sine x over x plus 1 squared times this group 1 over x plus cotangent of x minus 2 over x plus 1. Now here, the easiest way to start simplifying this perhaps might be to combine the right-hand side into a common denominator, is my thought. Let's see what I did here in the notes. Oh, no. You can see what I did here is I went ahead and distributed. When I distribute the x sine x over x plus 1 squared to the 1 over x, the x's will cancel in the numerator here with this x in the denominator. And I'll be left with sine x over x plus 1 squared. When I distribute to this cotangent of x, the sine of x will cancel in this numerator with the sine of x in this denominator, leaving just the cosine of x in the numerator multiplied by this x. So it'll be x cosine x over the denominator of x plus 1 squared. And that'll be minus 2 over x plus 1 times this quantity, where here there's nothing going to cancel, so it all just combines together to give you negative 2x sine x in the numerator with this negative 2 times this x sine x. And then this x plus 1 is one additional x plus 1 being multiplied by this denominator of x plus 1 squared. So that will become the quantity x plus 1 cubed. Now with this, I believe what I consider doing is rewriting it with a common denominator. And in fact, I think what I do is I combine these two over one denominator and then combine those to have a common denominator to match this term. Let's see if I'm right with that. Yes. That was my easiest way I could see into the process. So I went in and found a common denominator for those two terms, which produces this. And then what I need to do with this to get a common denominator to match this is multiply that numerator by x plus 1, so it produces this here. Right. Now, with this produced, is that my final form? No, I do a little expansion. If I expand the product of these first two factors, I will get x sine x plus x squared cosine x plus sine x plus the cosine x, right, with the expansion of these two factors. And then we're going to take away 2x sine x from that. We do have something canceling away here. Trying to see, I think, what do I do to move to the next step? Let me pause this for a minute and take a quick look at that. I can't quite tell what I'm doing, and I might have an error. So let me just double check this next step. Alrighty, folks. I think I found it. It was an error, in my opinion here. I think, not in my opinion, but in my calculation. Yeah, when I multiply these out, I do end up with these four terms as the product, right, of that, but binomial times binomial form. We are left with a minus 2x sine x at the end that comes from just this term here. Now, this first term, x sine x and negative 2x sine x, are like terms. So I was missing that term in this result. When combined, right? Negative x sine x minus 2x sine x actually leaves one negative x sine x. So it's negative x sine x. And I went ahead and reordered it with the x squared in the lead, x squared cosine x minus this x sine x when we take the difference of these two like terms, the x sine x and the negative 2x sine x. Those are the only like terms. I'll take those away from the x squared cosine x, and then I'll add on those terms given by, maybe I should just move this one up because that is an x term. Trying to group those terms together with the leading, the x decreasing in power down the line. All right, looking for pattern. All right, trying to show the pattern, a bit of a pattern there in the process, right? So yeah, just rewriting it, I might rewrite it like this, and in the end then just say, well, yeah, thus for y equal to x sine x divided by x plus 1 quantity squared, we do have our derivative dy dx is equivalent to this result seen here. Right? The result x squared cosine x minus x sine x plus x cosine x plus sine x, all divided by x plus 1 quantity cubed. That is the derivative of this y with respect to x, and we found that using a process known as logarithmic differentiation. Right? The process of logarithmic differentiation begins by rewriting, well, first applying the natural logarithm to our function, or equation that we want to find the derivative of, apply its natural logarithm, and apply the law of logs to both sides. Right? And what we might consider including here is maybe recalling our law of logs. Recall the laws of logs, where, what do we have? Well, not that. The log base, we want base b of an m times an n, right? Can be written as a log, we want base b of m plus, I'm going to make my life a little easier with these, a log base b of n. Right? We can write a product in the argument of a logarithm into the sum of two individual logarithms using the factors of that product. Right? That's one log. It's one rule that we use quite commonly in this process. The next says the log base b of m divided by n can be written as a difference of two logarithms involving m and n. Right? Again, order is important here in the quotient as well as it is in this difference. So if m is in the numerator, it is first in the difference in the argument of the logarithm for this difference. That's the other rule we're applying here. That's this quotient being split into this difference. Right? In a sense, we apply it to the difference first, which separates the two differences, and then we apply it to this product in the numerator that makes this the summation, right, in the numerator of that quotient. Right? And then lastly, the other rule we do apply is that if I have a logarithm of m and it's raised to a power of n, right, you can bring that n out in front as a constant multiple of your logarithm for just m. Right? And I do apply that here with this power of 2. When we take the difference of x plus 1 squared logarithm away from the x sine x here, I do bring that 2 out in front as a constant multiple using that law of logarithm. So let me go ahead and include those laws. All right. So we apply those first. That'll gets our right-hand side of our derivative, when we apply the derivative operator, what we might think of as a more efficient calculation. We don't have to do any product rule. We don't have to do any quotient rule. We don't have to do any chain rule. That's questionable, right? Or the arguable, because the chain rule is used in applying this fundamental rule. It says the derivative with respect to x for the ln of any function x is equal to f prime of x divided by f of x. We can apply that on the left-hand side and the right-hand side when we take the derivative of both sides. And we apply it on the left-hand side and the right-hand side. When we take the derivative of both sides, we end up with f prime of x over f of x on the left. And when we take the derivative of each of these terms on the right, we can see they're all going to be giving us f prime of x over f of x in each case. As for simplifying that, it becomes then just a bit of a game of algebra. We first solve for f prime of x by multiplying both sides by f of x. And just remember, f of x is your original function you're finding the derivative of. So right here is our derivative statement. Right? We should recognize that. Everything else from here on out is really just me performing a little bit of algebra to see if I can clean this up some. Right? Is there a way I can rewrite this to maybe write this simply as a single value, right? A single value, which actually ends up turning into a ratio value, right? With this summation in the numerator over the quantity x plus 1 cubed in the denominator, right? That is logarithmic differentiation, folks. It does kind of exploit our law of logs and that derivative result for the logarithm of a function, right? This derivative result seen right here. And it can be used to simplify sometimes some complex combinations of our rules, product, quotient, chain rule combinations. All right. So, yeah, that's just an additional technique known as logarithmic differentiation. I don't know, you might appreciate knowing this technique, and you certainly are welcome to use this technique when you feel it necessary, right? And you might be asked to use this technique. So, right, you might consider spending a little bit of time practicing it. All right. Other than that, folks, I have not much else to share with you in this video. And will I have another one for you here? I have one rolling around. We'll see. But if not, I will be back with certainly our next chapter of ideas, our next section of ideas, where we're going to start to look at application of the derivative. That's in our near future here, folks. I may have one more video I want to put together. I think that might be some useful information packed in there that we haven't really elaborated too much on in our notes that we might find useful. Let me think about that. I'll get that out to you here. But with that said, I'll end with this one, and I will see you in the next one.